Hey folks, welcome back. This time around I want to get into sort of some of the meat about what the course is actually about. Right? We've covered the administrative side of things. Now let's get into a little bit on compilers themselves. So for this session I want to just give a general introduction to compilers, the major phases, make sure that we're all on the same page moving forward. So, obviously our compiler is basically just one more software program. Right? It's just got a specific goal where we're trying to read code that's written in one language and translate it into something else. It might be translating it into machine code to run on a target architecture somewhere. It might be to translate it into a different target language. It might even be to read the code and translate it into the same languages we're in now, but with all sorts of optimizations thrown in or all sorts of customizations thrown in. So we've got this kind of as our main goal for our compiler, for our software. And then there might be a bunch of other secondary goals where we're trying to do things like say, okay, let's give the developer warnings about any problems or errors that might be detected in it. And so those are also concerns. So to do this, if we're dealing with the two different languages, right, our source language and our target language, then somehow our software needs to, quote unquote, understand both of those languages. So we are going to have to keep both of those pieces in mind as we're going through doing our development. And if we're talking about producing something that's going to be machine code, if we're actually trying to produce an executable, then you wind up needing fairly detailed hardware knowledge about the architecture that this thing's going to run on. If you're going to wind up handling pipeline and all sorts of memory hierarchies and different numbers of parallel processors and all sorts of other bits and pieces, then somehow you have to know about all that when you're writing the compiler that's going to produce code that hopefully runs well on that architecture. So there's a lot to go into this. All right, let's see. Couple of common variations for what I'm going to group into this sort of category of compilers. I'm going to include a lot of other things in this. So you've either got the idea where you're compiling something into an executable, right, where you're reading a bunch of different source code files and you're producing an executable that will eventually run on some target platform. Or maybe you're compiling something to an intermediate form where you're taking, code in whatever language it might be, and you're producing, let's say, Java bytecode. So you're going through and producing an intermediate form that isn't actually executable on its own, but that can be read by something else and executed. So you read your source code, you produce bytecode, and a virtual machine elsewhere runs that bytecode to carry out the execution itself. Or actually, I left off just straightforward translation here, going through and translating code from one high-level language into another high-level language, which is also a perfectly valid process for a compiler to go through and follow. Or the possibility that it's acting as an interpreter, where it's reading your source code statements and executing them one by one. So read the first instruction and run it. Read the second instruction and run it. Read the third instruction and run it. And that is actually a different process with different implications than reading the entire program, translating it as a unit, and then running the translated version somewhere down the road. So all sorts of different possibilities, and we'll try and discuss each of them as we go through the course. So just going back to those few basic ideas, you've got the idea where you're trying to compile to an executable, right? You're taking your source code or multiple source code files, piping it through your compiler, and it's producing the actual executable. Somebody runs the executable, feeds input into it, and it does whatever the program's supposed to do. Right? So that's obviously the one that we're most used to in terms of compilation. Or the possibility that you're doing something like producing bytecode, you're producing an intermediate form that's going to be executed by something else. So for instance, we stick our Java in, it gets compiled into an intermediate form, that gets fed into a virtual machine, and the user provides input as well that goes to that virtual machine, and it takes care of the execution here, if you like, and produces the output that you want. Right? So it's acting as either a further compiler or an interpreter, if you like, for the intermediate form and going through and saying, okay, let's read this stuff, read what the user wants to do with it, and then produce the results. Or there's the interpreter itself, where you've got the source code and you've got any additional user input that might be coming in. So the user's providing you with instructions and the user's providing you with input at the same time. You're just going through and saying, okay, well, for that instruction and this input, what do we do? And you execute that one piece, and you just cycle through that over and over and over again. So again, these are all things that we were all used to doing. We just want to make sure we're thinking about it in the context of compilation for now. Now, there's a ton of other software and a ton of other programs that we might make use of while we're going through and doing this. There's quite a few things that are kind of packaged together with compilers on a fairly frequent basis. And as a developer, we might think of these things as just one big lump. We are interested in this course in separating out the different pieces of them because they're each going to have their own role, and we want to understand what's done by each piece of the puzzle. Right? So you might have a preprocessor, for instance, that's going through and reading the source code and transforming it, applying macros, hash defines or templates or actual list macros or whatever it might be, rewriting the code before the actual compilation part takes place. You might go through and your compiler might take your transformed source code language and produce, if you like, relatively independent assembly language. Right? So for instance, taking a .cpp and compiling it into a .s file. Right? You might have an assembler that takes your assembly code and turns that into object code, right? Going from .s to .o, for instance. And then a linker and a loader that take all of those .o files, link them together, load it into memory to actually execute. So again, if you go through and you're using a reasonably sophisticated IDE, then all of this stuff is lumped together in your IDE, and you often don't see the individual pieces. You can recognize what they're doing if you're paying attention, but it's not something that you consciously think about all that often. So, in this course, we'll think about the individual steps a little bit more carefully. Then, in the actual compilation process, there's a pretty typical series of steps. Some of these get blended together, and depending on the specific compiler and the approach that you're using, the boundaries might be blurry here. But this is a fairly common approach. You go through and read the characters, right, the source code that you want to translate, that you want to compile. Maybe do some pre-processing on it. Then you go through and break that up, perform a lexical analysis. You break that up into the logical tokens for the programming language that you're interested in. So you might look at ABC and decide that ABC is an identifier. Or you might look at BEGIN and say, that's begin, right? That marks the beginning of some block. So you're taking the characters, grouping them into things, and then recognizing what that thing is supposed to represent. So the lexical analysis is going through and breaking the stream of characters up into recognizable tokens. Then we might go through and do sort of syntactic analysis, produce a syntax tree. Say, okay, well, that sequence of tokens represents, a function definition that's got an if statement inside it, that's got a while loop inside that. Right? So you break it up into what the logical construct happens to be. And then you might go through and do a semantic analysis and say, okay, well, there's the structure, if you like. It's a while loop inside a for loop inside an if statement, inside a function definition, inside my global program. But there's things beyond just the structure of it as well. You want to be able to do things like type checking and make sure that variables are declared before they're used and check the scopes of things. So all sorts of different things that have to take place beyond just the sort of syntactic structure. So we might take that syntax tree that we developed earlier and augment it, refine it to include semantic information, to include type and scope information. Maybe then we turn around and look at our, if you like, language-independent data structure. We've got something that's no longer source code, right? We've got this syntax, this augmented syntax tree, if you like, that's a representation of what this program is supposed to be doing. But it's no longer in the form of a programming language per se. So this intermediate generation stage is looking at how we can take that original source code program and represent it in an abstract fashion. So once we've got this abstract representation, eventually we can produce equivalent code in whatever our target language happens to be. So we might do a couple of things. First, we might go through and take that representation and do some optimization on it. Are there ways that we can optimize the code that don't depend on what eventual language we're trying to produce? So, if there's code that's unreachable, I can throw that away. If there's code that's highly repetitive, maybe I can replace that with the abstract idea of a function call, some sort of replacing the repetition, if you like. So if there's dead code, unreachable code, redundant code, maybe I can deal with that in this intermediate representation and rewrite the intermediate representation to be more efficient. Then eventually we want to take that intermediate representation and say, okay, now let's actually produce code in the language we're trying to target. So whether it's executable code or whether it's some other language that we're trying to translate it into. So eventually we go through and produce our target code, but we might break that up into multiple steps as well, where we say, okay, let's do the easy part first and just produce code that works. Having done that, we might then run a series of optimizations on that are dependent on the actual target platform, where we're saying, okay, if this is my sequence of instructions, is there some way I can optimize it to run on whatever the architecture happens to be? So you have these additional stages of optimization that you might be performing. And again, optimization can take into account lots of different things. We might be trying to optimize so that your executable is smaller, or so that it runs faster, or so that it uses less memory as it runs, or it produces fewer page faults as it runs. All sorts of different types of optimization that we might be interested in. So this is a pretty common breakdown of the steps that you might see in the compilation process. Now, again, every one of those steps can be incredibly complex, and there might be all sorts of different ways to do it, all sorts of different options and variations. We'll try and hit the highlights, hit some of the major options and big variants in those different steps as we're going through the course, but again, we could take any one of those steps and do a course entirely on that. So there's a huge amount of detail that we're just going to kind of introduce. We'll get into sort of the depths of a few bits and pieces, but there's a huge amount of this, or a huge amount to this beyond what we're going to cover in the course. Now, lots of times it's really helpful if we can share information across those different stages. If I can remember something from one stage and make use of it in a later stage. So we'll take a look at different data structures that we can use to augment this process and support this process, symbol tables and other things. And again, I think I mentioned earlier that this is kind of an arbitrary breakdown of the process into steps. Specific compilers and specific approaches are going to break things down differently and merge different pieces and do things in slightly different approaches. So again, we'll try and hit the highlights, but this is just an abstraction of one way to do things. All right, one of the things that we're going to need to do as we go forward with this is to come up with our own notation, our own syntax for talking about this process, for doing things like describing that intermediate representation. And so there are a variety of different forms of syntax that we're going to wind up looking at, and different forms of notation that we'll look at as we truck our way through the course. Now, there's also a variety of different tools that exist to help us in the development of compilers. So many of these are based on the idea of having some sort of formal grammar definition of the language that we're coming from and the language that we're targeting. So some kind of a formal grammar describing the rules for the source language and another grammar describing the rules for the target language. And the idea is, if we've got these formal grammars in whatever the notation might be, then maybe we can develop a tool that reads the grammars and then produces the compiler for us. So we'll look at the idea of a scanner generator. So this would be a program that reads a grammar and produces a lexical analyzer, a tokenizer, for that particular language. Something that could read a program in that language and produce the sequence of tokens that match that language, that match that particular program in that language. And this is essentially where Lex or Flex is going to come in that we'll look at next week. And there's also the concept of a parser generator, where it can read a grammar and can read a sequence of tokens, or pardon me, it can read a grammar and produce a syntax analyzer for us. So it can read the grammar for a language, produce a tool for us that could then read a bunch of tokens in that language and tell us what it meant. So this is where our Yak is going to come in, or Bison. So yet another compiler is the Yak. So we'll go through and look at scanner generators that read a grammar and produce a tokenizer for us, parser generators that read the grammar and produce a parser for us, and if we can put those two things together, then they can produce a compiler for us. So from the grammar for a language, we can just generate a compiler. And this is what we're going to be doing in the labs, as a matter of fact, is we're going to be working with Lex and Yak and coming up with a grammar for a language and producing a compiler for it from the grammar. And I'm going to be giving you a wonderful made-up language that we'll talk about next week that you're going to be building a compiler for. So, I guess to take these one step further, we could look at actual code generation tools where you feed in a collection of rules about how to translate one language into another, and it produces the actual translator for us. So all sorts of interesting ideas in terms of automated tools for compiler support. All right. I have another duplicate slide here, don't I? These are pretty much saying the same thing. I probably tweaked my wording, and that was about it. Well, lots of fun. All right. Well, where I wanted to wrap up is just thinking about compilers and languages and architecture in general and how they're interrelated. Right? The evolution of programming languages drives the evolution of compilers, just as the evolution of architecture drives the evolution of compilers. Somebody thinks up a brilliant new idea for a language or for a feature, or somebody comes up with a brilliant new architecture. Well, it doesn't mean much until we can get code to run on it, which means that somebody has to come up with the compiler technique that reads that feature and makes it work on that architecture. So very often you'll find that, advances in languages force us to make advances in compiler technology, and advances in compiler technology kind of enable us to make advances in languages. And you'll see places where the inability to come up with a good compilation approach, a good implementation for a language feature, really acts as a drag on the usefulness of the language. In the early years of C++, for those of us who are old enough to remember that, in the early years of C++, the language features were evolving and being described at a much faster rate than compiler developers could keep up. The language was described for years before there was a set of compilers that could really support it well. Right? Many of the features were broken or inconsistent, or wouldn't work the same way on two different compilers for the same language. All sorts of holes, simply because the compiler development was lagging behind the ideas that people had or wanted for the languages. So it's crucial to have people with a good understanding of this process. So to be good at compiler development, right, you've got to be good at software engineering because these are incredibly complex programs. You've got to be good with data structures because you're going to have to implement them. You're going to have to implement translations of them, and you're going to have to use them to make your compilers effective. You're going to have a good background in algorithms and complexity because, again, the techniques that we're using in writing our compilers tend to be incredibly complex, and they're solving different problems, and you need effective solutions, efficient solutions. Obviously, if you're writing a compiler that's going to turn something that's going to produce executable code, you've got to understand the hardware, the architecture that you're targeting. You've got to have a good understanding of language theory so that you're actually implementing things that do what's desired for the language and that do it effectively, that do it in a way that's going to be meaningful and helpful for that language. Again, there's all sorts of programming techniques that we wind up making use of in the process of producing our compilers. Dynamic programming is one of them. We'll go through and look at a ton of different techniques that we wind up using to try and make our compilers effective. So this is going to bring together all sorts of things from all sorts of areas of computing. Again, you need a decent background in all of it. It is a very challenging area, but a very rewarding area to work in. So I will leave that there for now. What we're going to do in the next session is come back and take a look at that sequence of steps in a little bit more detail, describe each of them in a little bit more detail, what's actually going on there. And then over the course of the term, we'll probably go back and spend a week or 2 weeks on each of those different phases as well to get into them in real detail. So there's the plan. I will leave it there for now.